This video is about the adiabatic lapse rate. First off, let's outline the simple adiabatic process. This is where there is no heat added or removed from the system, but the observed temperature changes. For example, when you spray an aerosol can, you probably notice that the air coming out is really cold. This isn't due to the contents of the can being really cold, but what's actually happening is that the air is coming out of a high pressure area inside the can and into a relatively low pressure atmosphere. This means that the gas expands, distributing the energy it has over a larger area. So therefore, the gas itself feels colder. In the same way, air is more dense nearer the surface of the Earth. Therefore, if a packet of air rises, it cools as it expands into the less dense space above it. The rate at which it cools is called the adiabatic lapse rate. There are two types. There is the dry and the saturated adiabatic lapse rate, known as the DALR and the SALR, or the DALR and the SALR. Let's start with the DALR. In unsaturated air, i.e. dry air, as air rises it cools at 3 degrees centigrade per 1,000 feet. As it cools, it condenses. Eventually, clouds will form. This is where we use the SALR. The dew point is the term given to the temperature where there is 100% relative humidity. In layman's terms, this is the temperature that clouds will form at. As clouds form, the lapse rate changes due to latent heat. As the air condenses, latent heat is released. So, as the air cools, once it reaches its dew point, because of extra heat being released, the rate at which it cools decreases. This reduced rate is the saturated adiabatic lapse rate, the SALR, at 1.5 degrees centigrade per 1,000 feet. Using this information, you can calculate the outside air temperature for a given altitude.